goal of this lab was to calculate the mass of a black hole based on the movement of a star around it. Assuming that the only force acting on the star is that of the black hole, we can use Newton's second law and Newton's universal law of gravitation to calculate the mass of the black hole. By using the provided location of the star's position and the time steps between each location, as well as the star's mass, I was able to calculate the velocity at each position and then the momentum. After calculating the change in momentum, I was able to determine the net force of the star, which is equal to the change in momentum divided by the change in time. In this video, I will discuss the fundamental principles and equations used in my calculations. I will then discuss my process for creating my model, which allowed me to calculate the mass of the black hole, which turned out to be 2.97186 times 10 to the 31st kilograms. The fundamental principles I used in this lab are Newton's second law and Newton's universal law of gravitation. Newton's second law states that the net force is equal to mass times acceleration. If we break this down, we can see that it is also equal to the mass times velocity divided by time. This, however, happens to also equal dp dt. Momentum is velocity times mass, and dp dt is the change in momentum over the change in time, which equals mass times the change in velocity divided by the change in time. From this observation, we are able to determine that dp dt and F net are equal to each other, thus making their components equal as well. Newton's universal law of gravitation is used to calculate the net force between two objects when they are the only objects acting on each other. This equation shows that the magnitude of the net force is equal to big G times mass 1 times mass 2 divided by the magnitude of distance squared, where big G is equal to 6.67 times 10 to the negative 11th. By using all three of these principles, we are able to calculate the mass of the black hole. To calculate the mass of the object, I began by calculating the change in velocity. Then I multiplied this velocity by the mass to get the momentum at this position. I calculated dp dt by dividing the difference between the previous momentum and the current momentum by the change in time. This gave me F net because F net equals dp dt. I then used Newton's universal law of gravitation to calculate the mass of the black hole, which turned out to be 2.97186 times 10 to the 31st kilograms. To create my model, I started by setting the mass of the star equal to 1.9890 times 10 to the 30 kilograms and change this time step to be 86,400 seconds, or 1 day. I used the previous calculations to get dp dt. Because I know from my fundamental principles that dp dt equals F net, I used the magnitude of the net force to calculate the mass of the black hole using universal law of gravitation. In my model, I also calculated the perpendicular and parallel components of both the F net and dp dt, which are the same. They are represented by arrows in the model. The yellow arrow is the F net, the blue arrow is F net perpendicular, and the black arrow is F net parallel. From our fundamental equations, we know F net and dp dt are equal to each other. F net equals F net parallel plus F net perpendicular. From Newton's second law, we know F net equals mass times acceleration. dp dt equals dp dt parallel plus dp dt perpendicular. From the momentum principle, we know that F net equals mass times change in velocity over change in time, which also equals mass times acceleration. Because they both end up equaling mass times acceleration, they must be equal to each other, and therefore their parallel and perpendicular components must be equal as well. If a new black hole with a different mass replaced the current one, and the trajectory of the star was still the same, we would not be able to calculate the new mass. Since the trajectory of the star is the same and the mass of the black hole is different than the original one we calculated, there must be another force acting on our system. If this was not the case, the star's motion would have changed. We cannot calculate the new mass because we do not know the force of gravity between the other objects acting on our system. In conclusion, from Newton's second law and the universal law of gravitation, we can calculate the mass of an object given the mass of the second object, the distance between the two objects, and the net force. Based on our fundamental principles, we know that the net force and its perpendicular and parallel components equal dp dt and its perpendicular and parallel components respectively. Because of this unique relationship, we were successfully able to create a model and determine the mass of the black hole.